Let's see if we have another one to practice. Here's another one to practice. We're going to try to balance this equation, right? Balance this equation. So what do we do to balance equations?
Create a little chart for ourselves.
That's right. We're going to create a little chart for ourselves. We're going to, what are we going to put on either side of that chart?
The different atoms.
Right. So first I like to write down the chemical form or the chemical reaction here, Na43PO4. Do you remember the name of that compound?
Is it? Let me look at my thing. Ammonium phosphate.
Yeah, very good. So you looked and you saw that it was the ammonium ion and the phosphate ion, right?
Yeah.
How about this compound right here that I'm writing, Ba3PO4?
Ba, is that barium?
That's right.
And that's phosphate. So barium phosphate.
Yes, that's right. Is it barium 2 phosphate?
What do you mean?
Well, sometimes we use Roman numerals. Do we have to use that for barium?
Um, it's a alkali earth metal, right? Second row.
That's right. So what's that mean?
We don't have to name it with a minor one or two, a Roman numeral.
Okay, good. So let's get in nice and close here. Yeah, barium is right here. It's in the second column, so it's always going to be a +2, so we don't have to call it barium 2 phosphate. All right, so we have our equation, and then we're going to write the different kinds of elements here on the left and on the right. Okay. Now, I'm going to let you try this one on your own, but I'm going to give you one hint before you go off and try it on your own. Okay. The hint is that instead of working with elements here, nitrogen, hydrogen, phosphorus, oxygen, barium, carbon, okay? Instead of working with the elements, if we look at the groups of ions and work with those groups, that will facilitate things a lot for us. If we can see on the left the ammonium ion, NH4, and then on the right we have ammonium ions. Here we have phosphate ions and phosphate ions. You see that?
Yeah, I see it. And then acetate and acetate.
That's right, acetate and acetate as well. And then barium and barium, right? So when we see those groups, if we keep in those clusters, I mean, if the chemical reaction keeps in those clusters, then when we balance it, we can keep in those clusters, right? So I'm going to look at ammonium ions on the left and right. I'm going to look at the phosphate ions on the left and on the right.
Doesn't a phosphate have a -3 charge?
Yeah, you could write that in there if you wanted to. It doesn't make a big difference here because it's just this, I'm just identifying the number of atoms of the different things, right? C2H3O2, acetate ions. Okay, so how many ammoniums do we have on the left?
3?
That's right. And on the right?
Just one.
Just one. Over here, phosphate?
1?
Very good. And then over here to the right, how many phosphates?
2.
Okay, barium?
1 and 3 over there.
Okay, and then here, acetate ions?
2 and 1.
2 over here and 1 over here. Okay, good. So that, working in those clusters will help us a lot, facilitate our lives a lot, or balancing, right? So that's a really good time saver if you do that. So go ahead and push pause and try to balance this equation, okay? All right. If you didn't know how to balance the equation, can't remember, and you hear enough to remind you, go ahead and push pause and take this opportunity to balance it. But what we need to do here is we see we have an imbalance, so I need to get more ammoniums on the right. So I'm going to do what?
Put a 3 in front of that ammonium acetate.
Okay, so this is ammonium acetate. So if I put a 3 there, cancel that out and cancels the acetate out. Now I have 3 ammonium and 3 acetate, like that. See that?
Yeah. Now the phosphate's next.
Right, so the ammonium is balanced, so we can move on to the next one. Phosphate, 1 over here, so what do I need to do?
A 2 on the left.
Okay, so on the far left here, a 2, and then that's going to change my ammonium, and that's going to change my phosphate, isn't it?
Yeah, you can have 6 ammonium and 2 phosphate.
6 ammonium ions and 2 phosphate ions. All right, that messes me up over here too as well.
Yeah.
So I could take care of that now or later. I might as well take care of it now. What am I going to need to do?
6 ammoniums, so on the right, so you need to change that 3 to a 6.
Okay, so I'm going to change this 3 to a 6. That changes my ammoniums and my acetates. 6 to 6, is that right?
Yeah.
All right, so, whoops, that 6 is a little bit high. Okay, so, ammoniums are the same. Phosphates are the same. Bariums aren't the same.
So you got to put a 3 in front of the one on the left?
I need 3 bariums, don't I? Yeah.
Yeah, so that changes the bariums and the acetates.
Okay, so it changes the bariums and the acetates. So now I have 3 and what?
6.
6 of those. Oh, look, I had 6 acetates over there as well. Good. Well, I'm done then. I finished, didn't I? The coefficients are 2, 3, 1, and 6. Right? Okay. Good job. Excellent job. 2, 3, 1, and 6 are our coefficients to balance that equation. Good. So this little method here, just separating things and lining things up, helps us be careful about our accounting. You're just going to make mistakes and miss problems in this type of scenario if you aren't organized, if you don't organize yourself well. So take the time to organize yourself well and count well and use the numbers, cross them out appropriately. Pay close attention. That's called paying attention to detail. Have you heard of that?
Yeah, I've heard of that.
Employers always want you to pay attention to detail. Okay, so here is a chemical reaction. This chemical reaction I can translate into English. We can think of it as in chemistry-ese, something like that. But this is 1 unit of calcium chloride aqueous plus 2 silver nitrates aqueous combines to yield a calcium nitrate aqueous and 2 silver chloride solids. Okay, so we translated it. Now remember that we've talked about this in class a little bit. If I had a compound, like let's use CaCl2 for our example here, and I wrote next to it aqueous, what does that mean?
It dissolved in water.
That's right. Aqueous means it's dissolved in water. And for ionic compounds, when you put an ionic compound in there, what does it tell us that it changes the conductivity of the solution by putting an ionic compound in there?
It means that the ionic compound dissociated into its ions.
That's right. It means that the ionic compound separated into its ion. What are the dissociative products when I put calcium chloride into water? I make a solution of aqueous calcium chloride. What are the dissociative products?
Well, I don't know what that means.
Well, that means like what are the resulting ions, right? I have the calcium ion and what?
Chloride ion?
How many chloride ions?
Oh, 2.
That's right. So I have the calcium ion, it's a +2. Look on the periodic table. And I have the 2 of these chloride ions. All right? These are what we call the dissociative products. They are aqueous. They are dissolved in water. All right? So I can throw those in there as well. But the dissociative products of calcium chloride is 1 calcium ion and 2 chloride ions. This is called dissociation, right? And dissociation is different than just dissolving. Sugar, ammonia, other molecular compounds dissolve, but ionic compounds, they dissolve and at the same time they're dissociating into their ions. Here's a little funny joke that I'll tell you over and over in this class. Here it is. If I put 1 gram of calcium chloride into this solution, right? 1 gram of calcium chloride, how many grams of calcium chloride do I have in there?
Well, it's a trick of some sort. It's got to be, I don't know, not 1.
That's right. It's not 1. In fact, the answer is 0. There's no calcium chloride because if this is an aqueous solution that results, that means I don't have any calcium chloride. I just have calcium ions and chloride ions floating around independent of each other. So there's no calcium chloride, but there's calcium and chloride ions. So when we see this, what this means is a solution of calcium and chloride ions. It doesn't mean there's any calcium chloride in there. We know the ratio because that was the compound that we put in there to start, right? But do you understand why it's important to recognize the difference there?
Yeah, I think I got it.
Okay, so what's this?
That's a solution.
Solution of what?
Silver ions to nitrate ions.
Silver ions and nitrate ions. And what's the ratio?
What do you mean?
Well, there's how many silver ions for every nitrate ion?
Well, what's that 2 in front mean?
Okay, the coefficient there, the 2, if I say I have 2 AgNO3, It just means I have two of these, right? Two of these. So it doesn't mean there's two silvers and one nitrate. That 2 means I have two silvers and two nitrates. So the final ratio is still just 1 to 1. The 2 coefficient in this scenario here is just there to allow us to get the correct ratio, because for every calcium ion, I'm going to need 2 nitrate ions. And for every silver, and if I have 2 chloride ions, I'm going to need 2 silvers. And for that reason, the coefficient goes there. We call this the molecular equation, and that's a horrible name because why do you think I think that's a horrible name?
Because those aren't molecules?
That's right. These aren't molecules. I prefer to call it the initial equation, right? But the molecular equation is the official name. And what the molecular equation is showing us is the kind of the recap of what's occurring. An aqueous solution of this and an aqueous solution of this is combined. And then another aqueous, in the products we have aqueous solution, but we also have a solid in the mixture. And this solid we call a precipitate. Mixing two solutions together and getting a precipitate. Now, we'll watch this video because it's super good. But what this is going to remind us is that ionic compounds come in this kind of a structure. What do we call this structure?
A three-dimensional lattice.
Very good. That's what we've talked about in class, a three-dimensional lattice. When I put this into solution, into water, it dissolves. It forms a solution. And that's because water molecules are surrounding the different ions individually, satisfying their charge, right? This is a chloride, negatively charged. These are sodiums, the white ones. Sodium ions, positively charged. Water molecules are surrounding them and taking them away, stabilizing that charge and allowing the ions to separate from each other. All right? This continues just on the surface initially, and then works its way in as more and more ions are exposed. Okay? So the result is dissociated ions, or what we call electrolytes. Have you heard the term electrolyte before?
Yeah, I've heard of it. It's when you buy Gatorade, it's got electrolytes.
Okay, so sports drinks often claim that they have electrolytes in them. Well, now we know what electrolytes are. What are the electrolytes?
Well, I didn't catch it. What are they?
Well, electrolytes is another name for the ions that result when a salt dissociates.
Oh, so electrolytes are ions?
That's right. For example, if I put sodium chloride in my solution, the resulting electrolytes are going to be the sodium ion and the chloride ion. Let me jot that down here. Putting sodium chloride into solution, AQ shows that it's in solution. The result is sodium ions in solution and chloride ions in solution. Okay. Molecular compounds like sugar, it dissolves as well. Water molecules separate the sugar molecules from each other, and a solid sugar will result in aqueous sugar. What do you think? If I put sugar into water, will it allow conductivity? Will it result in electricity being able to pass through the resulting solution?
Well, I don't think so. I remember we said that only ionic compounds, so that's molecular, right?
That's a molecular compound. And why is it that only ionic compounds and not molecular compounds?
Oh, I can't remember.
It's because of the ions. Sodium chloride dissociate, and we have ions, which would allow conductivity. Molecular compounds, when they dissociate, they'll become in solution, but they won't create conductivity. Okay, good stuff.